Welcome to the 22nd lecture of the course Representations of Finite Groups. Today we are going to talk about irreducible representations of symmetric groups. This will be the last lecture of this course, and the main theorem that we are going to prove today will give an explicit bijection between the set of conjugacy classes of a symmetric group and equivalence classes of irreducible representations of the symmetric group Sn. In lecture number 21, we define, given a partition lambda of a positive integer n, we have the set T superscript lambda of all lambda tabloids, where a lambda tabloid is an equivalence class of lambda tableau, and a lambda tableau is simply a Young diagram in which the numbers 1 to n have been filled in any order, and two lambda tableaux are said to be equivalent if and only if they have the same set of entries in each row of the Young diagram. Further, the symmetric group Sn act on this set T lambda of all lambda tabloids. We know that a symmetric group will map a lambda tableau into some other lambda tableau, and this action induces an action on the set of all lambda tabloids. So there is an action of the symmetric group Sn on T lambda, and therefore we can talk about the corresponding permutation representation. So let M superscript lambda be the complex vector space spanned by this set T superscript lambda. Then we have the permutation representation, which we denote by phi lambda, from the symmetric group Sn to GL of this complex vector space M lambda. You may recall that a permutation representation is almost never irreducible unless the size of the set on which the group is acting is singleton. So what we are going to do is we are going to find an irreducible constituent of this phi lambda that will serve our purpose. So let lambda and mu be two partitions of a positive integer n. Let T lambda be a lambda tableau, that is T lambda is a Young tableau of shape lambda. Define a linear map, we denote it by A of T lambda, from M mu to M mu, where M mu is a complex vector space spanned by the set of all mu tabloids. And what is this operator? So A of T lambda is take the sum over all the permutations which belong to the column stabilizer of T lambda. So recall that the column stabilizer of the lambda tableau T lambda is consisting of those permutations in the symmetric group Sn which keeps the column of this lambda tableau fixed. So for each permutation pi in column stabilizer of T lambda, you consider this sum, take the sign of this permutation pi, and then look at this map phi mu. Look here, phi mu is a representation of the symmetric group Sn into GL of M mu. So phi mu evaluated at the permutation pi. In case lambda and mu are the same partition, that is, if lambda is equals to mu, the element we denoted by E of T lambda, and what is that? That is, consider this operator A of T lambda and evaluate it on the lambda tabloid T lambda, the equivalent class of T lambda. And after plugging in value of the operator A T lambda, one can see that this is equal to sum of pi belong to the column stabilizer of T lambda into sine of pi, and then the operator phi mu of pi acting on the lambda tabloid T lambda. But notice that the action of the symmetric group on the tabloid is simply applying the permutation on the entries. So that is simply pi of the equivalent class of T lambda. And this element E subscript T lambda is called a polytabloid associated to the lambda tableau T lambda. Let P of lambda be the set of all polytabloids corresponding to the partition lambda of n. So what is P lambda? P lambda is this set. It consists of E of T lambda, where T lambda is a lambda tableau. Notice here that P lambda is a subset of the complex vector space M lambda. So what we are going to show that this subset is invariant under the representation phi lambda. If sigma is a permutation in the symmetric group Sn and T lambda is a lambda tableau, then phi lambda, the representation phi lambda from Sn into GL of M lambda evaluated at this permutation sigma is an invertible linear transformation of M lambda. Alright, so this will act on E of T lambda and it will map it to some vector in M lambda. In fact, it turns out to be same as E of sigma T, T lambda. Here, sigma of T lambda is simply image of T lambda under the permutations sigma, since the symmetric group Sn act on the set of all lambda tableau. So let us prove this. First notice that the column stabilizer of sigma of T lambda is same as conjugate of the column stabilizer of T lambda by sigma C T lambda sigma inverse. This follows because the lambda tableau T lambda and sigma T lambda are in the same orbit. So therefore this column stabilizer are conjugate. In fact, they are conjugated via the permutation sigma. So once we have this, then compute phi lambda evaluated at sigma, and we pre-compose this by this operator A of T lambda. Just plug in the value. What is this? So A of T lambda, as we defined in the previous slide, this is summation of pi belong to the column stabilizer of the lambda tableau T lambda, sine of pi, and then phi lambda evaluated at pi, but then we bring phi lambda sigma inside. So this is phi lambda of sigma and phi lambda of pi. This is here is composition of invertible transformation here. Now use this equality. Since pi is in the column stabilizer of T lambda, so therefore sigma inverse pi sigma is in the column stabilizer of sigma of T lambda. So doing that substitution, replacing tau by sigma pi sigma inverse, we get phi lambda of sigma A of T lambda is same as summation tau is in the column stabilizer of sigma of T lambda, and then sine of sigma inverse tau sigma, and phi lambda of sigma into phi lambda of sigma inverse tau sigma, which is same as summation as tau belong to column stabilizer of sigma of T lambda, and we know that sine of conjugate of tau is same as sine of tau, right? Parity doesn't change here, so it is same as sine of tau, and phi lambda is a group homomorphism, it's a representation. So phi lambda sigma into phi lambda sigma inverse tau sigma becomes phi lambda of tau sigma, which is same as summation tau belong to column stabilizer of sigma of T lambda, sine of tau, phi lambda of tau, and phi lambda of sigma. But now we notice here that this expression is simply A of sigma T lambda, which is same as A of sigma T lambda times phi lambda of sigma. Now to prove the assertion, evaluate it at T lambda. Consider phi lambda sigma of this polytabloid E of T lambda. That by definition is same as phi lambda sigma and E of T lambda by definition is same as A of T lambda of the lambda tabloid T lambda. But we know that phi lambda sigma into A T lambda is same as A of sigma T lambda, phi lambda of sigma, and acting on this lambda tabloid T lambda, which is same as A of sigma T lambda. And what is phi lambda sigma acting on T lambda? Phi lambda is the representation from Sn into GL of m lambda, and at a permutation sigma acting on the lambda tabloid T lambda, it is just action of sigma because it's the permutation representation. So this is the class of sigma of T lambda. By very definition of a polytabloid, this is simply the polytabloid E of sigma of T lambda. This is what we wanted to prove. So thus we have shown that the set of all polytabloids P lambda in the vector space m lambda is invariant under the representation phi lambda from Sn to GL of m lambda. So one can take the vector subspace of m lambda spanned by P lambda, and we can restrict phi lambda on this invariant subspace. The representation that we get is our desired irreducible representation. That of course we are going to show. Let lambda be a partition of n. Define S superscript lambda to be the subspace of m lambda spanned by the set of all polytabloids P superscript lambda. By the preceding proposition, S lambda is an Sn invariant subspace of m lambda for the representation phi lambda. Therefore, we can restrict phi lambda on S lambda. The restriction psi lambda from the symmetric group Sn to GL of S lambda of phi lambda is called the Specht representation of Sn corresponding to the partition lambda. The rest of the lecture will be devoted to showing that psi lambda is an irreducible representation of Sn. And secondly, to show that if two representations psi lambda and psi mu are equivalent for partitions lambda and mu of n, then lambda and mu have to be the same partition, that is lambda equal to mu. This will give a complete classification of irreducible representations of the symmetric group Sn. I want to make an important note here. So we say that S lambda is the subspace of m lambda spanned by P lambda, where P lambda is a set of all polytabloids. S lambda is simply a subspace spanned by P lambda. It is not true that P lambda is a linearly independent set. Let's see an example here. The set P lambda is not a linearly independent set. So let us take lambda to be the partition 1, 1, 1, so on, 1, a partition of n. The Young diagram corresponding to lambda is simply one column. So what is a lambda tableau here? Lambda tableau here is just plugging in the numbers 1 to n in this Young diagram. And therefore, what is a lambda tabloid? Remember, two lambda tabloid is an equivalent class of lambda tableau, where two lambda tableau are said to be equivalent if and only if they have the same set of entries in each row. But here in this particular Young diagram, each row has exactly one entry. Therefore, lambda tableau is same as lambda tabloid. And how many lambda tabloids are there? There are precisely n factorial lambda tabloid, because given a Young diagram with n boxes, one can fill the numbers 1 to n in precisely n factorial ways. In this case, lambda tableau are the same as lambda tabloids. Further, since lambda tableau are same as lambda tabloids, so what is the representation phi lambda here? Phi lambda here, recall that is the permutation representation corresponding to the action of Sn on the set of all lambda tabloids, which here in this case is the set of all lambda tableau, and which is a set of n factorial size, which is also the order of the group. So in this case, phi lambda is simply the regular representation of the symmetric group Sn. The column stabilizer of any lambda tableau in this case is whole of the symmetric group Sn. Since the Young diagram of lambda has only one column, it follows that the column stabilizer of any lambda tableau is the whole of the symmetric group Sn. That is, C of T lambda is simply Sn in this case for any lambda tableau T lambda. Thus, if we take any lambda tableau T lambda, what is the polytabloid corresponding to that? The polytabloid E of T lambda in this case by definition is summation as the permutation run in the column stabilizer of T lambda, which is just the whole of the symmetric group. So pi belonging to the symmetric group Sn, and then sine of pi times phi lambda evaluated at pi, but that is simply pi of the lambda tableau T lambda. Note that in this case phi lambda of sigma. So consider this representation phi lambda evaluated at sigma on this element of m lambda, which is the polytabloid E of T lambda. But E of T lambda we observed in the preceding slides has this expression. So it is phi lambda sigma of summation pi in the symmetric group Sn sine of pi of T lambda, but that is just phi lambda pi of the lambda tableau T lambda. We can bring this phi lambda sigma inside, and that becomes same as summation pi belonging to the symmetric group Sn sine of pi and phi lambda sigma phi lambda pi of the lambda tabloid T lambda. Since phi lambda is a representation, it's a group homomorphism. So phi lambda sigma into phi lambda pi is same as phi lambda of sigma pi. So as you vary pi in Sn, it is equivalent to varying sigma pi in Sn. Taking tau to be sigma of pi, we get that phi lambda sigma of E of T lambda can be written as summation tau in Sn and sine of pi, but pi is same as sigma inverse tau. So sigma inverse tau and phi lambda tau of the lambda tabloid T lambda. Since sine is a group homomorphism, sine of sigma inverse tau is same as sine of sigma inverse times sine of tau, but sine of sigma inverse is same as sine of sigma. So I can take it out, I can write it as sine of sigma and the rest of the summation as tau is in Sn and sine of tau phi lambda tau of the lambda tabloid T lambda. But what is that? That is just same as sine of sigma, and this expression is nothing but the polytabloid E of T lambda. So which is same as E of T lambda. We have shown that you take the representation phi lambda, evaluate at any permutation sigma on the polytabloid E of T lambda. This is simply sine of sigma times E of T lambda, which is just plus or minus times E of T lambda. Now recall that we proved a proposition today which say that phi lambda sigma of the polytabloid E of T lambda is nothing but E of sigma T lambda. But on the other hand, we have shown that phi lambda sigma of E of T lambda is plus or minus of E of T lambda, which implies that E of sigma of T lambda is equals to plus or minus of E of T lambda. Now notice that the symmetric group act on the set of all lambda tableau, and this action is in fact transitive. Now since Sn act transitively on the set of all lambda tableau, for any lambda tableau, let us say S lambda, there exists a permutation sigma in the symmetric group Sn such that I can write this S lambda as sigma of T lambda. So which implies that the corresponding polytabloid E of S lambda, which is same as E of sigma of T lambda, but that is just same as plus or minus of E of T lambda. This shows that the set of all polytabloids P lambda has two elements, Et lambda and minus Et lambda, and therefore the complex subspace of M lambda spanned by P lambda is just one dimensional. The subspace S lambda in this case is simply the vector subspace spanned by E of T lambda. Once we know that S lambda is a dimension 1 subspace of M lambda, what is the representation psi lambda in this case? We see that psi lambda in this case from the symmetric group Sn to GL of S lambda, which is just isomorphic to C star, is the sign representation of the symmetric group Sn, which being degree 1 is of course irreducible. So the point of this remark was to tell you that the set of all polytabloids is not a linearly independent set in general. In order to prove that each psi lambda is irreducible, we need to build up some more machinery in the form of small lemmas. Let lambda and mu be two partitions of a positive integer n. Suppose that T lambda is a lambda tableau and S mu is a mu tableau, such that look at the operator A of T lambda. So this A of T lambda is an operator from M mu to M mu, such that so A of T lambda acting on this mu tabloid S mu, class of S mu, it is non-zero. Then the partition lambda is bigger than or equal to mu in terms of the domination order. Notice here that A T lambda of S mu not equal to 0 implies that lambda bigger than or equal to mu. Interchanging role of lambda and mu, we will see that A S mu acting on T lambda not equal to 0 would imply that mu bigger than or equal to lambda. So therefore, if we have both the condition that the operator A T lambda acting on the lambda tabloid S mu is non-zero and the operator A S mu acting on the lambda tabloid T lambda is non-zero, then we will get that lambda is same as mu. So we are going to use this kind of small observations to show that if two representations are equivalent, then the corresponding partitions are same. Furthermore, if lambda is same as mu, then look at the operator A T lambda acting on the mu tabloid S mu. This is simply plus or minus of E of T lambda, this polytabloid. Let us prove it. So we shall use the domination lemma. Let me recall for you the statement of domination lemma. It says that if lambda and mu are two partitions of n, and if T lambda is a lambda tableau and S mu is a mu tableau with the property that entries in a single row of S mu lie in different columns of T lambda, then lambda is bigger than or equal to mu. So here I want to make a similar claim that lambda is bigger than or equal to mu, but under this kind of condition. So in order to use the domination lemma, I need to show that the hypothesis of the domination lemma hold. So I will show that this condition implies the hypothesis of the domination lemma and therefore lambda bigger than or equal to mu. Suppose that the hypothesis of domination lemma is not true. What does that mean? That means that there exists a row in the mu tableau S mu and two distinct entries in that which lie in the same column of T lambda. Consider the transposition Ij in the symmetric group Sn. What does this transposition do? Then consider the action of this transposition Ij on the mu tabloid S mu. But the action on tabloid is simply the induced action, so this is just same as equivalence class of Ij acting on the mu tableau S mu. But I and j are the same and are the entries in a single row of S mu. And this bracket denote the equivalence under the relation that two lambda tableau are equivalent if and only if they have the same set of entries in each row. Therefore, this is simply the mu tabloid S mu, and which I can think of as identity permutation acting on the mu tabloid S mu, which in terms of the representation implies that consider this representation phi mu, okay, from the symmetric group to GL of M mu, and this acting at the identity minus phi mu acting on the permutation Ij. When I applied this difference of these two transformations, mu tabloid S mu is therefore 0, right? It's just from here, this expression. Let us take H to be this subgroup consisting of the identity permutation and the transposition Ij. Then H is an order 2 subgroup of the symmetric group. Now since I and j, the entries I and j lie in the same column of the lambda tableau T lambda, this subgroup H is in fact a subgroup of the column stabilizer of the lambda tableau T lambda. Then H is in fact a subgroup of the column stabilizer of the lambda tableau T lambda. Since our groups are finite, so fix a set of left coset representatives of H in Ct lambda. So let sigma 1, sigma 2 and so on sigma k be a complete list of left coset representatives of H in this column stabilizer C of T lambda. I know that this Ct lambda then can be written as sigma 1 H disjoint union sigma 2 H disjoint union so on sigma k of H. Then let us do this computation. Consider this operator A of T lambda acting on the mu tabloid S mu. Write down the definition of the operator A T lambda, which by definition is same as summation as the permutation pi belonging to the column stabilizer of the lambda tableau T lambda and sine of pi phi mu of pi acting on the mu tabloid S mu. This is same as the following. So as we are varying pi in Ct lambda, but Ct lambda has this decomposition, so it is same as running from I to k, I from 1 to k. So I can write it as summation r from 1 to k and pi run over sigma I of H. But H has two elements, so it is going to have sigma I and sigma I composed with the transposition Ij. So this is going to be sine of sigma r into phi mu of sigma r plus sigma r times the transposition Ij. So sine of sigma r times the transposition Ij into phi mu of sigma r times the transposition Ij. All right, and this acting on the mu tabloid S mu. This can be simplified as summation r from 1 to k. And now notice here that sine of sigma r and phi mu of sigma r can be taken out. So this is same as sine of sigma r into phi mu of sigma r can be taken out. After taking out sine of sigma r and phi mu of sigma r common, here I can insert phi mu of identity, because phi mu is a representation, it's a group homomorphism, so phi mu of identity is identity. So I can write it as phi mu of identity, and sign of the transposition ij is -1, so it is minus phi mu of the transposition ij, again using the fact that phi mu is a group homomorphism. This acting on mu tabloid S mu. But just above we showed that this expression is 0, which is equals to 0 by star. This is star, which is a contradiction to the given hypothesis. Therefore, the hypothesis of the domination lemma must hold. Entries in a single row of S mu lie in different columns of T lambda, and therefore by domination lemma, lambda is bigger than or equal to mu. A contradiction to the given hypothesis. Hence, by domination lemma, lambda is bigger than or equals to mu. Let us prove the second assertion of the lemma. So let lambda equals to mu. That is, the partitions lambda and mu are the same. Under the given hypothesis of the lemma, we showed that the hypothesis of the domination lemma holds. That is, given these lambda tableau T lambda and mu tableau S mu, entries in a single row of S mu lie in different columns of T lambda. But recall that when we proved domination lemma in lecture number 21, we first proved another proposition. We showed existence of another lambda tableau U lambda, which has a property that columns of T lambda and U lambda have the same set of elements, and entries in the first I rows of S mu lie in the first I rows of U lambda. So let U lambda be the lambda tableau that exists due to hypothesis of the domination lemma and has the property that columns of U lambda and T lambda have the same set of elements, and entries in the first I rows of S mu lie in the first I rows of U lambda. Since lambda is same as mu here, taking I equals to 1, we see that entries in the first row of S lambda lie in the first row of U lambda. But the number of boxes in the first row of S lambda is same as the number of boxes in the first row of U lambda. Therefore, S lambda and U lambda have the same set of entries in the first row. Since the entries in the first two rows of S lambda lie in the first two rows of U lambda, but the first rows of S lambda and U lambda have the same set of entries, it follows that the second rows of S lambda and U lambda have the same set of entries, and so on. Or one can also apply induction on I, and we see that S lambda and U lambda have the same set of entries in each row. Therefore, by definition of our equivalence, this implies that the equivalence class of S lambda is same as equivalence class of mu lambda. Now, when we compute and we find that the operator A of T lambda acting on the mu tabloid S mu, which is actually the lambda tabloid, because lambda is same as mu here, this can be written as summation pi belong to the column stabilizer of T lambda, sine of pi, phi lambda of pi acting on the mu tabloid S mu. Note that the lambda tabloid U lambda and the original lambda tabloid T lambda have the same set of entries on each column, have the same set of entries on each column. So there exists a unique permutation sigma which actually fix the column. So this belongs to the column stabilizer of T lambda, so that the lambda tableau U lambda can be obtained from the lambda tableau T lambda by applying the permutation sigma. So sigma is an element of the column stabilizer of T lambda, and therefore when I multiply by this permutation sigma to each element of the column stabilizer T lambda, C of T lambda, I again get elements of Ct lambda. So I will replace this pi by tau of sigma inverse. So replacing pi by tau of sigma inverse in star, let us call this star, we get that operator A of T lambda acting on the mu tabloid S of mu is same as summation tau belong to the column stabilizer of T lambda, and then sine of tau sigma inverse phi lambda of tau and phi lambda of sigma inverse of the lambda tabloid S mu. But the lambda tabloid S mu is same as S lambda because lambda is mu. But the lambda tabloid S lambda is same as the tabloid mu lambda. I can plug in there. And furthermore, what is sigma inverse of mu lambda? Sigma inverse of mu lambda from this expression will be simply the tabloid corresponding to T lambda. Using all this information, what I get is summation tau belong to column stabilizer of T lambda, and of course I can write it as sine of tau times sine of sigma inverse and phi lambda of tau. Using double star and triple star, I know that phi lambda of sigma inverse of the lambda tabloid S lambda, which is same as the lambda tabloid mu lambda, is same as the tabloid T lambda. But this is same as sine of sigma inverse, which is plus or minus 1 times summation tau belong to column stabilizer of T lambda and sine of tau. But what is phi lambda of tau? This is simply tau acting on the tabloid T lambda. And now if we look at this expression, this by definition is the polytabloid E of T lambda. So this is just same as plus or minus 1 of E of T lambda. This is what we wanted to prove. Our next observation is the following. Let lambda be a partition of n and T lambda a lambda tableau. Then image of the operator, look at this operator A T lambda, which is defined from the space m lambda to m lambda, is one dimensional. In fact, it is generated by this polytabloid E of T lambda. Recall here that m lambda is a complex vector space spanned by the set of all lambda tabloids. Proof. Note that by definition the polytabloid E of T lambda is A of T lambda acting on the lambda tabloid T lambda, and hence E of T lambda, the polytabloid E of T lambda, belong to image of this operator A of T lambda. So one way implication is immediate. Conversely, if S lambda is any lambda tableau such that A T lambda acting on this lambda tabloid S lambda is 0, then there is nothing to do. If A T lambda acting on the lambda tabloid S lambda is not equal to 0, then by the preceding lemma, this A T lambda of this lambda tabloid S lambda should be plus or minus of Et lambda, which of course belong to the complex vector space spanned by Et lambda. This completes the proof of the lemma. Our next result is the following theorem. Let lambda be a partition of n and V an Sn invariant subspace of the representation space M lambda of Sn. Then either S lambda is a subspace of V or V is a subspace of S lambda perp, the orthogonal complement of S lambda. First, notice that we can consider the representation phi lambda from of the symmetric group Sn to GL of M lambda as a unitary representation. Further, if T lambda is any lambda tableau, then consider the adjoint of the operator At lambda. Then A of T lambda, its adjoint. What is this by definition? Write the definition of At lambda. That is by definition is summation pi belong to column stabilizer of T lambda sine of pi into phi lambda acting on pi and take its adjoint. This is simply a finite sum of these operators phi lambda pi's. So adjoint will go in. This is just same as summation pi belong to column stabilizer of T lambda sine of pi phi lambda pi its adjoint. But our representation is unitary. Since the representation phi lambda is unitary, it follows that phi lambda pi into phi lambda pi star is same as identity, and which is also same as phi lambda pi star into phi lambda pi. The definition of unitary operator, which implies that phi lambda pi star is simply phi lambda pi inverse, which is same as phi lambda of pi inverse, because phi lambda is a group homomorphism. So therefore this expression becomes summation pi belong to column stabilizer of T lambda sine of pi and then phi lambda of pi inverse. So replacing pi inverse by tau, this expression is same as summation tau belong to column stabilizer of T lambda sine of tau inverse, but which is same as sine of tau into phi lambda of tau. But what is this? This by definition is simply A of T lambda again. What does this show? This shows that the operator A of T lambda is a self-adjoint operator. So this fact we are going to use to prove the theorem. So there are two cases. We proceed in two cases. First one is as follows. Suppose that for all lambda tableaux T lambda and all vectors V belonging to this vector space V, we have that A of T lambda of the vector V is 0. Consider the inner product of the vector V with the polytabloid E of T lambda. Plug in the expression for the polytabloid Et lambda, which is same as V inner product with the operator At lambda acting on the lambda tabloid T lambda, which by definition of adjoint operator is same as A of T lambda adjoint acting on the vector V, this lambda tabloid T lambda. At lambda is a self-adjoint operator, so therefore this is simply same as A of T lambda acting on the vector V inner product with the lambda tabloid T lambda. But here we know that A of T lambda acting on the vector V is 0. So therefore this has to be 0. This implies that for any lambda tableau T lambda and for any vector V, the inner product of V with the polytabloid Et lambda is 0. This implies that the vector V, the vector space V is sitting inside the orthogonal complement of the subspace spanned by all these polytabloids Et lambda, which is simply S lambda. So it is sitting inside S lambda perp. Let us consider the second case. Suppose that there is a lambda tableau and a vector V such that the operator At lambda acting on that vector V is non-zero. This in particular implies that the vector V itself is non-zero. Since V is Sn invariant and the operator At lambda is what? It is simply the sum of pi belong to the column stabilizer of T lambda and sine of pi representation phi lambda operating at the group element pi. And V is Sn invariant, therefore phi lambda pi of any element of V will again fall in V. In particular, At lambda acting on any element of V will again fall in V. It follows that At lambda of the vector V in fact belong to the vector space V itself. On the other hand, by the preceding lemma, image of the operator At lambda for any lambda tableau T lambda is this one-dimensional vector space C of E T lambda, where T lambda is a lambda tableau. This implies that At lambda of the vector V belong to C of this polytabloid Et lambda, and which further implies that At lambda of this vector V therefore belong to V intersection with this one-dimensional vector space spanned by the polytabloid Et lambda, which is of course here non-zero by our assumption. Therefore, what is the possibility? Because C of Et lambda is simply a one-dimensional vector space spanned by the polytabloid Et lambda, and V intersection C of Et lambda is non-zero. This implies that the polytabloid Et lambda belong to the vector space V. Now recall that for any permutation sigma belonging to the symmetric group Sn, the polytabloid E of sigma of T lambda, this is the operator phi lambda of sigma acting on the polytabloid E of T lambda. But here we just showed that E of T lambda belong to V, therefore, and V is Sn invariant, therefore phi lambda sigma of Et lambda also belong to V, which implies that E of sigma of T lambda also belong to V for every permutation sigma belonging to Sn. But Sn act transitively on the set of all lambda tableau. For any lambda tableau, the polytabloid E of S lambda look like E of sigma of T lambda for some T lambda, which implies that S lambda is contained inside V. Thus, we have shown that for the Sn invariant subspace V of M lambda, either S lambda is contained in V or V is contained in S lambda perp. This completes the proof of this theorem. Once we have this theorem, we can now prove that the representation psi lambda, where lambda is a partition of N, is an irreducible representation of the symmetric group Sn. As a corollary, we get this very important result. If lambda is a partition of N, then the representation psi lambda of Sn into GL of S lambda is irreducible. Let us write down a proof of this. Now it is just a one-line proof. Let V not equals to S lambda be an Sn invariant subspace of S lambda. By the preceding theorem, either S lambda is contained in V or V is contained in S lambda perp. But S lambda cannot be contained in V, otherwise V would be same as S lambda. So it follows that V must be contained in S lambda perp, which implies that V is contained in S lambda intersection S lambda perp. which is of course the trivial subspace, and therefore psi lambda cannot have any proper Sn invariant subspace of S lambda, and hence psi lambda is irreducible. Now we are halfway through. What remains to show that these psi lambdas form a complete list of inequivalent irreducible representations of Sn. For that, we need to show that if lambda and mu are two partitions of n, and psi lambda and psi mu are equivalent representations, then lambda has to be mu. Now, it remains to show that if lambda and mu are distinct partitions of n, then the irreducible representations psi lambda and psi mu are inequivalent. Once we do that, then our classification of all inequivalent irreducible representation of the symmetric group Sn would be complete. So we need some more machinery here. Let lambda and mu be partitions of n, and let T be a morphism. So T belonging to home Sn of phi lambda, phi mu. T be a morphism from the representation phi lambda to the representation phi mu. If S lambda is not contained in kernel of this morphism T, then that lambda is bigger than or equals to mu in terms of the domination order. Further, if lambda is mu, then consider the restriction of T on this subspace S lambda of M lambda. This T restricted to S lambda is scalar multiple of the identity, equals to alpha times identity for some alpha in C. Since T belong to home Sn phi lambda phi mu, kernel of T is an Sn invariant subspace of M lambda. By the preceding theorem, we know that any Sn invariant subspace of M lambda satisfies the property that either S lambda is contained in this invariant subspace, or this subspace is contained in the orthogonal complement of S lambda. But we are already given here as hypothesis that S lambda is not contained in this invariant subspace. Therefore, the invariant subspace must be contained in S lambda perp. By the preceding theorem, we have that kernel of T should be contained in S lambda perp. Therefore, for any polytabloid E of T lambda, T of E T lambda should not be 0. But T is a morphism from phi lambda to phi mu. So 0 not equals to T of E T lambda. Plug in the value of E T lambda, which is T into A of T lambda acting on the lambda tabloid T lambda. Since T is a morphism, it follows that A T lambda also commute with T. So this is same as A T lambda of T acting on the lambda tabloid T lambda. Now the element T of this lambda tabloid T lambda, this is in the representation space of phi mu, which is M mu, and therefore it should be a linear combination of some mu tabloids. So element T of T lambda belonging to M mu is a linear combination of basis elements, because M mu is the subspace spanned by mu tabloids. But the operator A T lambda of T T lambda is non-zero, which implies that there exists at least one mu tabloid such that A T lambda of that mu tabloid is non-zero. Now since A of T lambda acting on T of this lambda tabloid T lambda is not equal to 0, there exists a mu tabloid S mu such that the operator A T lambda acting on this mu tabloid S mu is not equal to 0. By a lemma proved earlier in this lecture, it follows that the partition lambda is bigger than or equals to the partition mu. This is what we wanted to prove. Let us consider the second part now. For the second assertion, suppose that lambda equals to mu, then compute the following. Consider the operator T acting on the polytabloid E of T lambda. Plug in the value of the polytabloid E T lambda, so that is T times the operator A of T lambda acting on the lambda tabloid T lambda. But since T is a morphism and A is a finite sum of the images of the representations at the elements of the column stabilizers, so therefore A T lambda also commute with T, which is same as A of T lambda of the operator T acting on the lambda tabloid T lambda. But this is image of the operator A T lambda, and we proved a lemma a while ago that image of the operator A T lambda is of dimension 1. In fact, this falls in the complex vector space spanned by the polytabloid E of T lambda. But S lambda is the subspace of M lambda spanned by polytabloid, so this is certainly contained in S lambda. What does this imply? This implies that T of any polytabloid Et lambda falls in S lambda, and S lambda is the vector subspace of M lambda spanned by the set of all polytabloids, which implies that T keeps S lambda invariant. Okay, notice here that T in this case belong to home Sn phi lambda phi mu, but phi mu is phi lambda here because lambda is mu. That is, T is a morphism from M lambda to M lambda with this commuting property that T phi lambda of pi is same as phi lambda pi of T for all pi belonging to Sn. And what we have just shown that T keeps this subspace S lambda of M lambda invariant. So therefore one can restrict T on Sn. Thus one can restrict T on S lambda, and T restricted to S lambda from S lambda to S lambda is a morphism. That is, T belong to home Sn of psi lambda psi lambda, and we know that psi lambda is an irreducible representation. Now since psi lambda is irreducible by Schur's lemma, T equals to alpha times identity for complex number alpha. This proves the second assertion. We now prove final two results of this lecture. Let lambda and mu be partitions of a positive integer n. Then the following hold. The first part is the following. If the set home Sn of psi lambda phi mu is non-zero, that is, there exists a non-zero morphism from the representation psi lambda to the representation phi mu, then the partition lambda is bigger than or equal to mu in terms of domination order. Furthermore, if the two partitions are same, that is, if lambda equals to mu, then the dimension of the space of morphisms home Sn from the irreducible representation psi lambda to the representation phi lambda, this is precisely 1. Second assertion is the following. The irreducible representation psi mu appears with multiplicity 1 in phi mu. Let's prove the first part. So let T belong to home Sn of psi lambda phi mu such that T is non-zero. T is a non-zero morphism from the irreducible spec representation psi lambda to the representation phi mu. Then as an operator, T is a map from S lambda to M mu. We extend T to a linear map, let us denote it by T tilde, from M lambda to M mu by setting T tilde of any V plus W is simply T of V, where V belong to S lambda and W belong to S lambda perp. Of course, here I am taking M lambda as S lambda direct sum S lambda perp. One can easily check that T tilde is a linear map from the representation space M lambda to the representation space M mu. And in fact, we can see that it's a morphism. We check that T tilde of phi lambda sigma acting on a vector V plus W by definition is same as T tilde of phi lambda sigma of V plus phi lambda sigma of W. But we know that the representation phi lambda keep both S lambda and S lambda perp invariant. So therefore, the second factor falls inside S lambda perp anyway, and this falls inside S lambda. By our definition of T tilde, this is same as T of phi lambda sigma of V. But T is a morphism from the representation psi lambda to phi mu. Notice here that psi lambda is simply phi lambda restricted to S lambda. So therefore, this is just same as phi mu of sigma of T acting on V. But that is same as phi mu sigma of T tilde of V plus W. So which implies that this extended map T tilde belong to home Sn of phi lambda phi mu. By construction, it follows that S lambda is not contained in kernel of T tilde, because T tilde is simply an extension of T, and T is a non-zero morphism. So T is not zero on whole of S lambda. So therefore, T tilde is also not zero on whole of S lambda, and therefore S lambda is not contained in kernel of T tilde. And therefore, by preceding lemma, it follows that lambda is bigger than or equal to mu. Let us prove the second part of the first assertion. If lambda equals to mu, then again by preceding lemma, a morphism T belonging to home of Sn from psi lambda to phi lambda is scalar multiple of the inclusion. But what does this imply? This is scalar multiple of the inclusion. So writing phi lambda as a direct sum of irreducible constituents, of which psi lambda is certainly 1, it follows that dimension of the space is precisely 1. Let us prove the second assertion of the theorem now. The second assertion of the theorem follows immediately from assertion 1. Since dimension of this space of morphism home Sn psi lambda phi lambda is 1. We now prove the main result of this lecture, which is also the last theorem of this course. Specht representations psi lambda, where lambda is a partition of n, form a complete list of inequivalent irreducible representations of the symmetric group Sn. We have already shown that Specht representations psi lambda, where lambda is a partition of n, are irreducible representations of Sn. To show that psi lambda is not equivalent to psi mu for partitions lambda and mu of n, it suffices to show that if they are equivalent, then the partitions must be same. So let lambda and mu be partitions of the natural number n, and suppose that psi lambda is equivalent to psi mu. By Schur's lemma, the space of morphisms from the representation psi lambda to psi mu is then non-zero, in fact is of dimension 1. So the space home Sn of psi lambda psi mu is non-zero, in fact it is dimension 1, but this is of course contained in the space of morphisms from the representation psi lambda to the representation phi mu. because psi mu is simply a restriction of phi mu on S mu. So therefore, the space of morphism from the representation psi lambda to phi mu is non-zero. Hence, by preceding theorem, lambda should be bigger than or equals to mu. But lambda and mu are arbitrary partitions of n, and interchanging role of lambda and mu will give mu bigger than or equal to lambda. But domination order is a partial order, so it is anti-symmetric, which implies that lambda should be same as mu. Thus, we have shown that if the irreducible Specht representations psi lambda and psi mu are equivalent, then the partitions lambda and mu must be same. And hence, the set of all Specht representations psi lambda, where lambda is a partition of n, form a complete list of inequivalent irreducible representations of the symmetric group Sn. So this theorem gives an explicit bijection between the set of conjugacy classes of the symmetric group Sn and a complete set of inequivalent irreducible representations of the symmetric group Sn. A very beautiful result. There are a lot of more things that one can say about representations of the symmetric group here, which I am not going to do. For example, what is the degree of the representation psi lambda? That is still an interesting question, and there is a nice formula for the degree called the Hooke formula, which I am not going to do in this course. Lot of interesting research is still going on in the representation theory of symmetric group. So this is the last lecture of the course on representations of finite groups. I will stop here, and I may be uploading more videos on my channel regarding general mathematics, mathematics research in future. Thank you.